So we can move on. So the next talk will by Samuel Arsac, who will speak about their project about adhesive category theory for graph rewriting in Rocq. Please.
Thank you. Hello, everyone. Well, I will start by telling you about what is graph rewriting, and then tell you about my formalization. So, graph rewriting is a framework that is used to apply some rewriting rules to graphs. So, of course, there are many kinds of graphs. So you can have simple directed graphs, or directed multigraphs, hypergraphs, or you can have graphs with typed graphs. So for example, you can add colors to vertices. So in order to abstract over all these different kinds of graphs, we'll use category theory. So there is a framework called double push-out semantics. It's not the only one. It's not the only categorical framework to do that, but this is the one we are interested in. And so here is an example. The rule is at the top. So this is, you can say this is in the input, this is the output. So what this rule does is that it takes a graph with two vertices, one self loop, and it will delete the self loop and add an edge between the two vertices. Here I use colors to show you how the morphisms map vertices. And then, so we can inject the input, have the injection of the input into the graph we wish to apply it in. So just a very simple example here with an additional vertex. The first thing we do, so notice we have an intermediate object here. We take what's called a push-out complement. If you're not very comfortable with category theory, it's not really a problem. The rest of the talk will mainly not be about that. So we take an object such that this whole square is a push-out. And then we can take the push-out on the right side, and we get the result of the application. So I forgot to tell you, here we are in multigraphs, directed multigraphs. Of course, if we were in simple graphs, then it would be a bit different. We would have a single edge between the two vertices on the right. Okay, so double push-out rewriting mostly uses pullbacks, push-outs, and various types of monomorphisms, such as regular monomorphisms, which are a slightly stronger notion. And more importantly, we have to define the classes of categories which have the right properties in order to have interesting results with regard to graph rewriting. So the strongest notion that we have is adhesive categories, which are nice because it's easy to prove that a specific category is an instance of an adhesive category. However, there are also weaker notions, such as RM adhesive categories. Here, RM stands for regular monomorphisms. I'm not going to go into the details of the axioms that we have in each class, but in adhesive categories we talk about monomorphisms in general, and in RM adhesive categories we switch to regular monomorphisms. So it's a bit weaker. It has harder proofs. It's harder to prove that a specific category is RM adhesive, but it has the same interesting properties that we expect from adhesive categories. And finally, we have RM quasi-adhesive categories, which are the weakest notion. Rather simple proofs, essentially same level of difficulty as adhesive. But some properties, some theorems in the literature are only proven for RM adhesive categories and not for RM quasi-adhesive, so we might lose some nice properties. However, it's still important because some usual categories of graphs are only RM quasi-adhesive, such as simple directed graphs. So our goal is to organize these notions into a library and formalize some major graph rewriting theorems. So I will highlight two main points of our formalization, and then I will talk about what we have formalized. So the first problem is how you deal with equality. If the initial approach, the naive one, would be to use Rocq's default equality and add some axioms to do what we need in some places, so which are very standard, so proof irrelevance and functional extensionality. And so we would get something like this for a category. So we have an object, we have a type of object, and the home set takes two objects and gives us a type. And then if we want to state associativity, assuming we have defined the composition in the dots here, then we use simply the equal sign. So this is nice for many use cases. However, we run into issues, for example, if we want to define the subcategory of split monomorphisms. So split monomorphism is a morphism which has a retraction R, so a morphism R such that R composed with M is the identity, so a half isomorphism in a way. So if we want to define this category, we'll have our split monomorphisms are a morphism and a proof that it has a retraction, but that proof involves some computational content, which is the retraction that we might want to use later, knowing that we have a split monomorphism. However, when this retraction is not unique, but when we compare two split monomorphisms, we want to ignore what this retraction is. We would just want to compare the underlying morphisms. And that is a problem if we use this approach. So the solution to that is to use what is called e-categories, which rely on setoids. So instead of having equality, you have an equivalence relation. And so you change your definition of category to something that would look a bit like this. So instead of having a type for the home set, you have a setoid. And so if you state now some equality like associativity of composition, instead of having equality, you replace it with equivalence. The downside is that now you have to prove that any function between home sets respect the equivalence relation that you have defined. However, now whenever we define an instance of a category, we can choose the right equivalence relation that fits our need. And this is nice because now we have a completely axiom-free theory, and we still keep the right notion in each instance. So another thing is that our formalization has two hierarchies of notions. So on the left, we have, so I talked about adhesive, RM quasi-adhesive categories. So there are a few additional structures here, but these are the main ones. But we also have a more complicated one, which is the hierarchy of morphisms. So with morphisms, basic morphisms at the bottom, the usual monomorphisms just above, and then regular monomorphism, split monomorphisms, and isomorphisms at the top. And we also have the notion of adhesive morphism, which is more specific to adhesive category theory. So this requires a way to organize these notions correctly. So for that, we use a hierarchy builder, which is a tool that is developed alongside the MathComp library, and which implements coercions and canonical structures in the right way, instead of you having to do that by hand to obtain nice properties, such as the fact that if you prove something in a low level in the hierarchy, for example, let's say we prove a lemma about all monomorphisms, then we can apply that lemma to a split monomorphism, for example, without saying anything, just giving the split monomorphism as an argument instead of a monomorphism. And the tools put in place by a hierarchy builder will allow you to do that transparently. It also allows for some extension for extendable hierarchies. However, so you can notice here that there is a dashed row instead of the usual ones. So hierarchy builder still has limitations compared to what we would have liked to achieve. So this arrow here is not does not exist. In reality, it's a bit more complicated than that. But outside of this specific thing, we have a nice way to organize our hierarchies. So for formalized results, we have formalized several characterizations of RM adhesive and adhesive categories, which are long proofs to give equivalent definitions for these categories, which are used to build instances in our hierarchies. And we also have formalized two main theorems. The first one is called the local charge Rossin. So it says that parallel independence of two rule applications is equivalent to sequential independence. If the idea of parallel independence is that the two rules are applied to the same graph, but they do not interfere with each other. And sequential independence, well, you apply first the first rule, then the second rule, but the application of the first rule does not interfere with the application of the second one. This is the idea, and so this theorem says that the two notions are equivalent. And the concurrency theorem details when and how you can compose rule applications. So this is more, here we talked about sequential independence. The concurrency theorem is more about the case where two rule applications are dependent sequentially. And so both of these theorems are true for RM quasi-adhesive categories, so they are true for the whole hierarchy of adhesive categories. We also have formalized instances. So, of course, and so here I show you the axioms that we use for each instance. So we have types and functions, which require constructive definite description, which is a weak form of choice, and predicate extensionality, which is a mix of functional extensionality and prop irrelevance, but a bit weaker than that, than the conjunction of both of them. And so it is, of course, adhesive because types and functions, topos and more. Setoids, which are more setoids and function that respect the equivalence relation, which are more interesting because they are RM quasi-adhesive without any axiom. If we want them to be RM adhesive, we have to add the axiom that we can lift this junction to sum. And finally, if we want them to be adhesive, this time we have to use a constructive indefinite description, which is a stronger form of choice. But the interesting part is that we have proven that these axioms are strictly necessary. So the axioms are equivalent to setoids being adhesive or adhesive. We have also formalized finite types, which work without any axioms. Simple directed graphs. Since we rely on types, we have to use the same axioms. We just do types and we add edges. And as I said at the beginning, they are not adhesive or adhesive. So these are for the basic instances. Now we also have constructions to define more instances. So if so a category of functors from category C to a category D is adhesive if D is adhesive without any axioms. We have no proofs for the case where D is RM adhesive or D is RM quasi-adhesive. However, I'm pretty sure this is not true, but I think this requires a very little additional hypothesis on the category. But the important part is that since we have the case since it is proven in the adhesive case, we can have categories of presheaves, which are functors from category C to category of sets, so we can use types, for example, which gives us the fact that any category of presheaves is adhesive. You can do a lot of things with presheaves, for example, directed multigraphs, or undirected multigraphs, or hypergraphs, can be all defined as categories of presheaves. And we also have slice categories, which are nicer, so they preserve adhesivity at each level. And they allow to do type graphs. If you choose the right object to do your slice on, then, for example, you can color your graphs, give color to your graphs. This is not a graph coloring here, but you can enforce a number of properties. And so these are for instances. And so we have a library with, so first, some general category theory without any axioms, which is a bit more than 5,000 lines. Then specifically, we have the theory of adhesive categories, still without any axioms, which is 2,400 lines, more or less. The proofs for the local Church-Russell and concurrency theorem was, I think, 400 lines in total. And for reference on paper, they take 1.5 and 2 pages respectively, with a lot of space dedicated to stating the required definitions to state the theorem. So 400 lines is pretty reasonable considering the size of the proofs and statement on paper. And finally, we have instances that I just talked about, and which is quite a large part of the code with more than 2,000 lines. So in total, the whole library is about 10,000 lines. For future work, we would like first to have a category where we can compute pullbacks and push out efficiently and adapt the whole library so that the relevant results can compute. So actually this is having a category of pullbacks and pushouts efficiently computed is now mostly done, but I still have to update the rest of the library. Another goal would be to develop a way to transport results along category equivalents and also along adjunctions. This is a more long-term goal. And this is it. Thank you, and I'd be happy to answer questions if you have any.
So, thank you, Samuel. Other questions? Yes, so there's one question there. Thank you.
Hi. Thanks for the talk here. I had a questions on the instances, for instance, for simple graphs. So if I understood correctly, you take graphs that have any type as underlying type, and then you need all these axioms to be able to manipulate these arbitrary types.
Yes.
But could you have instead a category where you restrict the underlying type to have, for instance, decidable equality or things like that, and then be able to avoid needing these axioms?
Yes, you could avoid, well, if you change the underlying category, for example, you could take a